So now we'll look at the Gauss Seidel method. The Gauss Seidel method, like the Jacobi method, is just an iterative method. And if I want to be more detailed about this, the Gauss Seidel method is essentially just a variation of your Jacobi method. So what I've written in these three equations are the three equations that we have from the Jacobi method. So if you look at these three equations, when we actually do the Jacobi method, we are going to first of all calculate the value of x1 at k plus 1 based on the first row of the equation. Okay, so you can see once we perform this row, or once we calculate this operation, we are going to have the value of x1 at k plus 1. With Jacobi method, you're going to carry on with row 2 and then row 3 to find x2 and x3. But what the Gauss Seidel method says is that since from our first row we already have the solution of x1, why don't we place this solution into the x1 here to calculate x2 at k plus 1. Alright, since you already have a new value of x1, we might as well just substitute this back into x1 in the second row. And if we already have x2 at k plus 1 from row 2, why don't we include it into this value here? So that is the Gauss Seidel method. It's a variation of Jacobi method, but the variation is such that it uses the new value or the new solution for x whenever you have it. So if that is the Gauss Seidel method, and if I want to write the equation for the Gauss Seidel method, then this is easily becomes x1 at k plus 1, x1 at k plus 1, and this becomes x2 at k plus 1, because whenever we get new values, we're going to use the new values in the next calculation. So here I've shown it only for x1, x2, and x3. If you have a 10 by 10 system, the same concept is going to be applied, where whenever you get new values for x, you are going to use it for the calculation of the other x values. So that is the essence of the Gauss Seidel method. If I extend this equation to okay, before I do that, let me show you something. So let me get rid of all of this first. Alright, so if you look at the equations for the Gauss Seidel method for a 3 by 3 system, you can see that for the first row, these are the values that multiplies to the coefficient matrix A, and you can see that x2 and x3 are evaluated at level k, which is the initial guess or the old value. But when we look at the second row, when we calculate x2 at k plus 1, you can see that x1 here is actually multiplied to a21, and x1 is the new value, whereas x23 is multiplied to x3, where x3 is the old value. And if you look at x3, you can see that both x1 and x2 are the new values, and they are multiplied to a31 and a32. So what I'm trying to show you here is this. If I rewrite the coefficient matrices, I will get something like that. You have a11, a12, a13, 21, 22, and 23, and here you have 31, 32, and a33. Alright? So if you look at the first row says that x1 at k plus 1 can be obtained by using the values of x2 and x3 at the old value. And x2 and x3 are multiplied to a12 and a13. So where's a12 and a13? This is a12 and a13. And these two values are multiplied to the old value of x. When you look at row 2, a23 is multiplied to the old value. So where's a23? This is a23 over here. Alright? At the same time, a21 is multiplied to the new value of x1. So where is a21? This is a21 over here. If you look at row 3, a31 and a32 are multiplied to new values. So with regards to the system matrix, this is a31 and a32. So what we can conclude from here is that the old values are always multiplied to the upper triangular half of the matrix. So this is the upper triangular matrix. And these three values, or this set of the upper triangular elements, are always multiplied to the old value. On the other hand, new values are always multiplied to elements from the lower triangular matrix, which you can see from here. So all those although this is done for a 3 by 3 matrix, the same concept can be extended if you have an n by n system. So what does this actually mean? It means that we can generalize our Gauss Seidel method this way. So in general form, our Gauss Seidel method can be written as this. So you have 1 over aii representing the diagonal elements. You have your right hand side vector minus the summation from j equals to 1 to I minus 1 of aij xj. So let me write it in terms of Jacobi method first. So in terms of Jacobi method, you have this, and then you have the j equals to I plus 1 all the way to n of aij xj. So if you look at the previous recorded lecture, this is actually your Jacobi method. And I've told you guys that we need to split it for the convenience of Gauss Seidel. Why is it? If you look at the summation term here, this summation term of this aij basically represents the lower half of your matrix, whereas this particular summation of aij represents the upper half. This is indicated by the I minus 1 and I plus 1 in the summation index respectively. Alright, so if you go back to the Gauss Seidel method, because all the new values are always multiplied to the lower triangular matrix, and since this is the lower triangular matrix, when we generalize our Gauss Seidel method, we can easily call this xj at k plus 1. And on the right hand side, on the last term here, which is your upper triangular matrix, you are going to multiply this to only xjk. So this right here is the expression for the Gauss Seidel method. And this is also the reason why we would prefer to write our Jacobi method in this particular form, because it makes the implementation of the Gauss Seidel method very straightforward. So this you would probably see the application when you actually carry out your lab 1. So I hope you'll be able to learn or use whatever you have learned here to carry out your lab 1.